Hello and welcome to 2022. Those of you who saw our previous videos have probably been waiting with bated breath for our sequel to the 360-degree robot radar video, in which we promised some source code examples. We were briefly going to recap on the design and development of the hardware. However, when we began filming, we noticed that our 3D printer was misbehaving. The final prints were very ugly and uneven. Even looking back at this footage, we can see that at the start of the builds, they are stringy, bobbly and uneven. If we had have noticed this by even a few layers, we would have stopped the print. After a close inspection, we found this crack on the right side Z bearing. Not sure if this could cause the problem we are having, but we don't have time to find out just now. Then somebody showed an interest in our project and talked us into selling our test rig. So we have made this video for you to be getting on with, partly with new footage and partly with archive stuff. After this video is published, we will build a new rig for more development and tests. So for the hardware, you may want to look at our previous videos. I will include the links in the description. And please visit our website at so-now.com/robotics/radar for videos, parts lists, STL files for those with 3D printers, and of course to find the source code listings described in this video. And so, as promised, the code. We are using an Arduino Nano to position our sensor and gather the data, so why not use the Arduino compiler to do the job? A look at the first few lines of code shows we are using the new ping library to drive our sensor, the HCSR04 ultrasonic ranger. First we include the header file. Then we have to define which of the pins on our Arduino we wish to use to interface with our sensor. Once those pins are defined, we can create an object of type newPing with the name Sonar, which we will use to refer to it later in the code. This line is just a comment reminding us of the value of pi. We will not be using it here, but it may come in handy later. Here we define the Arduino pins we will be using to control our stepper motor using the ULN2003 stepper driver. The last highlighted line declares an integer variable iMotorSpeed. We use this later to add a slight delay to prevent our stepper randomly skipping steps. Next, some global variables. iStep count keeps count of the current step. I counts per rev, 512 in our case. iLookup is an 8-element array to hold the pin configuration for each of the steps required to turn 1/512th of a rotation, i.e. one step. Use this variable to keep account of radians covered so far. If this value rolls past 2 times pi, reset it to 0. In our setup function, we configure our motor pins as outputs, then configure and open the serial port. That brings us on to our main program loop. Inside this loop is a for loop. Since we want to rotate our sensor one step, take a measurement, 512 times per revolution, the for loop controls the program flow, restarting after I counts per rev, in this case 512 steps. We first make a call to this global function. Its purpose is to move the sensor one step. We will look a little closer at this soon. We next increment our radian angle. If the angle is greater than 2 times pi, we have completed a full rotation reset it to 0. We then attempt to get a range from our sensor. If there is nothing in range, the sensor will return 0. Now all that's left to do is to export our data to anybody listening. We are using a serial port to transmit our data. We create a string object. This is not the most efficient way to use strings in C, but it is quick to code and works okay for a program this size. We create a string with a comma delimiting each field. Then we print the string to the serial port. Now you may remember the clockwise function we mentioned earlier. Let's have a closer look at that. We have another for loop, this time with 8 steps. And for every one of those steps, we call another function, setOutput. The setOutput function writes the binary data to the stepper controller to cause it to move forward the correct number of stepper microsteps. In our case, 8 microsteps equals one of our desired full steps. And as we mentioned earlier on, if we don't add a brief delay in between steps, the stepper randomly misses steps. That concludes the section on the Arduino code. Upload it, open a serial port, and you should be able to test that it's all working. And on to the processing code. We chose processing for several reasons. It is free to download. It is based on the Java platform, which is quite common. When you get stuck, it has a good website over at processing.org. Also, several of our viewers asked for examples written in processing. Presumably, it has become more common and many more programmers are using it. To be fair, it is now 2 years since we worked on this code, so some of the more complex equations are long behind us. We will try to explain what we can, but the program works as is, so if you are unsure, make some changes, see the result, see if you can understand it better. If it breaks, revert to the original version and break it some more. We will start at the top. The processing development environment is similar to the Arduino IDE. The bare bones application has a setup function and a main program loop. In Arduino, the main program loop is called loop. In processing, it is called draw. One of the intended purposes of the processing language is for developing graphical interfaces. If we click the Run button in this empty sketch, processing creates a window for us. This window is not big enough for our project. Our radar screen will have a size of 400 by 400 pixels. We also want a 1 pixel border around the edge. So we will set our window size 402 by 402 and set the background to black. We are going to be using an image object to draw our radar on, so we need to declare it as a type of P image, which we will refer to as radar later. Create the image in the window, and later we will need some transparency for fading pings and stuff. It seems the image does not have alpha channel by default, and the only way to add it is pixel by pixel, so the for loop here does that for each pixel in the image. Frame rate sets the desired refresh rate. The image command actually places the image on our window, and the set location positions the window on the physical screen. and there's nothing to see here so far. As said before in this video, the data is sent to this app using the serial port. The next block of code is explained in the comments. Basically, list the available ports for debugging, select the first available one, empty the buffer of any junk which may be there so far, and none of the serial code will work unless we import the serial library. Let's do that now. And we need to add the global variables required to make it work. That concludes the setup steps. Now on to the main program loop. In some cases we would not yet have a data source, so we may create a temporary application to provide sample data. In our case, we have a sonar antenna providing real data. Let's start by capturing the data from the sonar. This application is pretty much event driven. If there is no data in the buffer, do nothing. Again, plenty of comments help us to follow along. While bytes of data are available, read them into our string variable until we read an end of line character. Double check that we have some data. We pass this data into some variables for use later, and since we may use this data in other functions, we make the variables global and declare them at the top. One thing we need to take care of is that our data is sent to us as comma-separated values. We create an array of values from the data and copy each element of the array into our variables. Having got this far, it should be possible to test the data transmission and reception. So we add some debug code to print our data to the debug window. And as we can see from the lower left of the console, what appears to be meaningful data. Now it's time to begin plotting our graphics on the screen, and we are going to make a separate function for that. We will name it sweep and declare the function. Now, in order for us to plot a point on our screen, we need the angle and range. The angle and range is given to us by the sonar. We need to use the sine and cosine functions to define the angle on the screen. Then we need to throw range into our calculations and plonk a blob on the screen in the right place. Don't forget, the angle and range is given to us. What we are calculating here is the perceived position on the screen. Unfortunately, processing would not let us use the set function to plonk a blob. We didn't have time to find out why or how. We did find out, however, that processing would allow us to draw a line, so we cheated and used a short line to draw our ping. There we have real data being projected on the screen. It is, however, persistent. That is, once it is drawn, it stays there. If we turn the antenna assembly 45 degrees left, new data is drawn to the screen. 45 degrees to the right, the screen is becoming quite cluttered. We need some way to remove old data in the same way as would a real radar. One way to do it in processing is to create a tint. In this case, black, but semi-transparent. Then apply it to the image each program loop. This overlays our current image, making it dimmer each time. As we can see, it works, but too fast. We need to slow it down. Adding some code to apply the tint, wait for a few program loops, then apply it again, slows down the fading effect. We need a couple of global variables to keep track of how many loops have occurred since our last fade. Okay, looking a little bit more plausible. A few more lines of code will make it more realistic. Some radar screens have a highlight line to indicate where the antenna is pointing. We will create a simple line from the center of the radar screen to the edge based on the current angle. And I think we'll add it to the sweep function. Here we calculate the angle from the center to the edge. The plus 0.08 in these lines draws the line just a little ahead of the real angle. This prevents the green line overwriting our pings. Set the pencil colour, set the pencil thickness, draw the line. Looking a little more realistic, one more addition to finish it off. We will let you go through this last function to figure out what it does and how it does it. Add a call to our new function. That concludes the 360-degree Robot Radar 2022 video. I hope everybody can get something from it. Please like, subscribe, and most important, leave a comment. Check out the links to the previous videos. I will add them to the description. Visit the website for file download links and updates to the project. And as always, thanks for watching.